the introduction, Dr. Mattingly. That is a long history. You're right. It doesn't feel that long from this side of things, but yeah, that's where we start. I'm going to go bring up my presentation here, and it should come up. So you should see my screen coming over, and there we go. I think at some point I must have given you the wrong title for my dissertation because it was optical and optoelectronic and transport properties of indium nitride. So most of my
Oh, really? Well,
on indium nitride.
you'll have to, the LinkedIn has the wrong title then.
Oh, let's fix that one then. Thank you. So basically what we're going to be talking about today is the growth and characterization of indium nitride. And I am set to not go long. The timer up here is going to turn off at 1:30, so just before 1:30. So we should be out of here in time today. The reason that we are talking about these materials is because they're interesting. So group 3 nitrides, indium nitride being one of them, is a crystal structure. You can see some pictures here. You can see gallium nitride on the left here. You can see, sorry, that's aluminum nitride on the left. Gallium nitride, and there should be a laser pointer popping up. Is it broken now? No, might be broken now. Gallium nitride on the bottom right and indium nitride on the top. Now, the reason that I have the powder form of indium nitride is because that's how it was discovered. People made this powder, and they kind of ignored it. That powder discovery happened back in the 1920s and 1930s. The reason that I care about these materials is because a lot of other people care about them. The group 3 nitrides were actually awarded, particularly gallium nitride and indium nitride, were awarded the Nobel Prize in Physics in 2014. Every time you go to Walmart, every time you look for a new light bulb nowadays, they say LED on them. And the foundational technology is this 3 nitride technology. Gallium nitride emits a high energy blue light, which can then be absorbed by a phosphor or something like that, and then re-emitted to create white light. They're significantly more efficient. And the reason that I care about indium nitride, so we can turn them into devices. LEDs, avalanche photodiodes, so these are detectors. Transistors that work with very high energy applications so that they can deal with high current throughput. And the reason I care about indium nitride is because it is the third in this class of materials. So you can see at the top left, there's aluminum nitride up here. And aluminum nitride has a band gap, which is an energy absorption level of about 6 EVs. And what that means is that if I have ultraviolet light, it can absorb that energy and produce an electron that can move around. Or if I give it enough electrical energy, it can emit a photon at that energy. Gallium nitride is sitting at about 3.4 over here. Looks like there are the lasers again. Gallium nitride is sitting at 3.4, which is just above visible, but we can drag it down ever so slightly into the visible, and that then works very well for emitting light like the LEDs that we talk about. Indium nitride is all the way down here, and it was discovered to have a band gap of about 0.7 to 0.9 in 2000, so fairly recently. And if we can get these class of materials, aluminum nitride, gallium nitride, and indium nitride to work together, we can generate structures or devices that then can detect not only in the UV, in the visible, and in the infrared, but they're all the same class of material. So now you can mix them together and you can create detectors that are not only here, there, and there, but anywhere along these lines. So these things have great potential. And you can see compared to the current technologies we have and have been using, that there is a big potential for advancement here. So the first question I'm going to ask is, what is a metal or conductor? I honestly didn't know the answer to the question of what is a semiconductor really, till much later than I probably should have if I tell my teachers here. And the first thing is a metal. A metal is just a material where the electrons are free to roam above the material. So you can see I've made these little electrons. They're floating above the material. They can move freely. They're loosely bound, and I can transfer energy or electrical energy across them. And they can, sorry. I'm watching my screen and seeing the slides freeze, so I can kind of see what you guys are seeing. So the electrons can just move freely across and transfer energy across the surface. Now we can talk about an insulator. In an insulator, I have wells. And these wells are a result of the periodic structure or the crystal nature of the material. And the electrons are trapped deep down inside these wells, all very low energy down here. So if I want to get these electrons out of the well, I need to raise the energy all the way up in order to get them out here. So typically when we talk about insulators, we're talking about energies of 9 to 10 volts that I needed in terms of materials that I'm talking about. That may not always be the case, in order to get the electron out of that gap. Finally, we talk about semiconductors. In semiconductors, you can see that the well that these electrons are trapped in is much smaller. So now, instead of using huge amounts of energy in order to get a single electron out, I can get multiple electrons out with very low energies. So these energies can then pop out. Sorry, that was not zoom in. These energies can pop out and then travel freely across the top like a conductor does. What this allows us to do is to create selective conductivity. Having the ability to have selective conductivity basically creates a switch which can then be used to create electronic devices. And the way that we represent this most of the time is with a simple band diagram. We have on the bottom a valence band where the electrons are stuck. They're in valence with the atoms. On the top, we have a conduction band where the electrons can jump up into that band and be moving around freely. And in the middle, we have what's called the band gap, the energy of the gap. So that EG right there is the amount of energy necessary to move from this valence band to the conduction band. So I mentioned crystal. The group 3 nitrides have a crystal structure that's called a Wurtzite crystal structure. It's 2 hexagonal patterns. So you can see a single hexagon pattern up top here. My laser pointer comes in. There you go. You can see a single hexagon on top here. You can see another hexagon sitting right underneath it. The first layer here would be the group 3, which would be our metal. So that would be gallium or indium or aluminum. And the bottom layer here would be our nitrogen. And if I stop moving the screen around, I'll get the laser. There you go. So these here will be nitrogen. And this structure is stacked across space. So I have a huge amount of these hexagons layered across an entire layer. I have another layer coming down of the next layer of hexagons. And then in order to get a repeating structure beyond that, I offset my layer of hexagons. So this here is just one triangle from this hexagon up here. So if you look at that single point there, that would be the gallium or indium atom on the left, on the right, sorry. And then it'll connect to these two to make that same triangle that you see down here. So now I have this repeating pattern all the way across. I just see Dr. Bosman's chat pop up here. If you guys have any questions, please feel free to put them in chat. We'll get to them when I decide to take a break from talking. I've got a big mouth. And now my slide won't move anymore. There you go. So you saw that valence band and conduction band that I showed you there for a simple case of a semiconductor. But when we start to look at the valence bands and conduction bands for other materials, they definitely do not look that simple. You can see right here for indium nitride, top left, this top band here would be the valence band that we care about, and the band up top here would be the conduction band. And this here forms the energy gap for indium nitride. You can see in these pictures, the band gap for indium nitride is fairly small. We can move up to gallium nitride, it gets a little bit larger. And we get up to aluminum nitride, and it's even bigger again. Again, this shows us that each of these materials takes much more energy to get an electron to be free to travel within it. So, again, going back, I said back in the 1920s, 1930s, indium nitride was produced as a powder, and that wasn't particularly interesting. So when the semiconductor revolution happened, we started dealing with materials like indium phosphide, gallium arsenide, and all these things. And so the nitrides again started to get more interest. So back in 1989, they produced indium nitride. And this time they produced it more, pardon me, as a crystal. So again, we're sitting with a structure that once produced on multiple layers up to form this material that we have on the left. On the right, we produced it again. And this time they produced it at extremely high pressures. Again, just making indium nitride. So how do we make these materials? This is the fun part about going to Georgia State. They have an entire room that's about the size of this laboratory, this classroom, dedicated into making these materials. They had 2 reactors, and this is the first reactor. This is a metal organic chemical vapor deposition reactor. You can see all these pipes coming in here. These are gas flow pipes coming in. On the top here, there is a optical control section, optical control unit that has optical access down. And on the bottom inside there, where that bright light is where we would grow the material. Inside there, there is a wafer carrier. So this platform right here is the wafer carrier. You can see a top-down view of it. Oops. It has 3 holes in it, or 3 pockets, where we would put a sapphire wafer. So that's a 2-inch disc of sapphire. Into the reactor, we'd let in our gas that would be containing gallium or indium or aluminum. And we'd also let in our hydrides. Sorry, the hydrides are the ones with the aluminum gallium. And this would be the one that would carry in our nitrogen. It would be cooled at the top so that we didn't get deposition of our material up there. And then it would be heated down here. So this here was heated up to 1100, 1200 degrees Celsius in order to get the chemical reactions to happen that would make these materials. And the way that we did it would we bring in our material. So we'd bring in nitrogen with hydrogen, ammonia, and we'd bring in gallium, in this case for this reactor, with a methyl group. So this is called trimethyl gallium. And these chemicals would be brought into the reactor. We'd heat them up, so we'd give them energy to break them apart. So we'd split off the methyl groups. We'd break up the ammonia, and we would get a layer of gallium with nitrogen forming on the bottom. And the goal is to form multiple layers of this material. And chemical vapor deposition, or MOCVD, is very good at doing that. We can get growth rates on the order of microns per hour. Now, that doesn't seem very fast, but in the crystal growth world, it actually is pretty fast. And this is what we're getting. You can see nice crystal structures here. You can see these layers, followed by another one. I'll get the laser pointer working. Another layer, another layer, another layer. And each of these is a single layer of material stacked on top of each other. From this picture right here, we can actually determine the lattice structure, part of the lattice structure of this material. You can determine how thick each layer is, and so you can know what your constants of your lattice are. There's also some pretty cool things right here. If you look on this picture, there's these holes right here. And those holes are called pinholes. And around them, you can actually see a screw dislocation. So what that is a layer of crystal that spirals down. Instead of being 2 separate layers, it makes its own second layer. It's not what we want to see, but it is something to cool to look at. And the problem with this process is that it works nicely for aluminum nitride. You can see here up at 1,000 degrees, we can grow aluminum nitride. Gallium nitride, we can grow at 1,000 degrees. But with indium nitride, we're kind of stuck, because as soon as we get above this right here, these materials just stop growing. And this is a problem that we've had evidence of since basically 1989, when we started growing this material. This paper was published in 2008, and they were still dealing with this issue. So until recently, as in 2015 probably, this material wasn't grown above 600, 650 degrees Celsius, which is a big problem if you're trying to mix it with aluminum nitride and gallium nitride that are grown at 1,100 or 1,200 degrees Celsius. So that was one of the problems that I was working with. Can high-quality indium nitride be grown in conditions that are suitable for gallium and nitride to produce heterostructures or to produce alloys? So a heterostructure is when I layer 2 different materials, such as gallium nitride, and then I put a layer of indium nitride on top of it. Alloys would be mixing gallium nitride and indium nitride in the same material to make gallium and indium nitride together. So what we did was we had a second reactor that we've been working on since about 2015 again. This reactor was a plasma-enhanced or migration-enhanced plasma-assisted MOCVD reactor. So again, metal organic chemical vapor deposition. But on top of that, we used a plasma source instead of using other materials. This reactor looks very similar. Again, you can see we have a wafer carrier down at the bottom here. That wafer carrier was a little bit different in shape. It didn't have the same 3 pockets because this was more of an experimental reactor. We didn't want to waste as much material trying to do the same thing 3 times and having it not work. And it also had a lot more access for spectrometers and other gases. So since the other reactor was designed for one specific purpose, it did that well. It's well established. We didn't mess with it. But with the reactor that we wanted to play with, we could make any changes we want. So we did the changes we wanted. And the way that this process works is instead of just using ammonia, we use direct, laser pointer again, we use nitrogen ions. So now we can go ahead and just dump all of this material at the same time, all this material into the reactor at the same time, and now I don't need to worry about breaking apart my ammonia, which it turns out ammonia is actually one of the biggest problems to growth at higher temperatures. Ammonia needs high temperatures in order to break apart, but since we don't have high temperatures for indium nitride, we had to figure out another source of nitrogen. And we solved another problem by doing that too. So as we move forward, in order to grow indium nitride, we then get the indium split apart from its methyl groups, and we can then deposit nitrogen directly onto it. So as we grow these structures by layer, we can put down some indium. We then deposit nitrogen with the plasma. Then we can put down another layer of indium, and we can put down another layer of nitrogen ions. Ions. So that's exactly what we do. We deposit a little bit of nitrogen. We then let the methyl groups dissipate, and we then expose it to plasma. So we are almost building this material layer by layer. And this is actually the term for a process called atomic layer deposition. And that is what we didn't want to do because that is extremely slow. So we sped this up, and we may have been a little bit sloppy with allowing the methyl groups to clear and trying to move this from a experimental, slow procedure into a procedure that can be used for production. And that is exactly what we did. We grew layer upon layer. And you can see now that what we did was we experimented with a lot of variables. We had the metal organic pulse width, which is the time that we allowed the indium, or the trimethyl indium, to come into the reactor. As it goes through the gas lines, it will dissipate a little bit and spread out. So you're not dealing with just a single on-off pulse, but it spreads out over time and then floods the reactor in that shape there. And then we would let it dissipate and get onto the surface. And then we would excite it with plasma and expose it to the nitrogen that came from the plasma. After we did that, we'd move on to characterization. Because if you're growing material and you don't know what it looks like or what it's doing, you basically don't have any idea what you're doing. So the first thing that we did was we'd do normal incidence spectroscopy. And what that did was that produced a interference pattern that was related to the thickness of the material. You can see we had a fiber optic on the left that would shine down, and the light would bounce up through this material and come back up and be collected coincidentally or coaxially with the same fiber, and then broadcast to our computer from the spectrometer. And you can see here that we have these interference fringes. And this is very similar to something like Newton's rings, counting the rings up that you see in the interference pattern. That is basically what this is, except instead of using the same wavelengths of light, we're using multiple wavelengths with the same thickness and seeing how they interact with the thickness rather than changing the thickness for the same wavelengths. We did FTIR, Fourier transform infrared spectroscopy, which gives us those same wavelength related features that happen at higher energies, but they also give us the features that are related to the crystal structure. So these features that you see down here are related more to the way that the material actually absorbs light due to the spacing in the crystal. So because the crystal is a word-type structure, some of these features here, so you can see this is just our sapphire curve up the top here, some of these features that are in sapphire get changed up because of the indium nitride, and they're absorbed differently because of the indium nitride. And we also have some other features down here that are interesting. So these things all play a factor in how do we understand this material is behaving. We look at Raman spectroscopy. Raman spectroscopy is just, pardon me, the low energy absorptions that are, again, due to the crystal structure. I expose the crystal to high energy light. I catch the reflected light, and instead of looking at the pure elastic reflection, I look at the inelastic reflections. And I can judge how much energy shift the inelastic reflection has had, and that correlates to these shifts right here. So this is not truly a wave number plot, but a wave number shift plot. And you can see right here, and right here, I had light that was absorbed and re-emitted at a slightly different energy than I started off with. And they correlate again to the structure of the material. This one here particularly correlates to how good the crystal structure is. How uniform is it? I had some fun with this machine at Georgia State. You can see here back in 2018, I took some data from our machine, and we took some data from another machine that was a professional grade machine. And there was a bit of a problem. You can see they didn't line up. So after spending a couple months fighting with the machine, I got them to line up. That was fun. The other thing that we did was X-ray diffraction. Now, some of you may have seen upstairs, we have a little X-ray machine. It's just a tiny bit smaller than this one over here. This one takes up most of a office space. The one upstairs sits on a bench top. So they work the same, though. It's kind of interesting. What happens is X-rays are shone onto our sample, and the waves will interact with each layer of the material. And as they interact, we again get diffraction patterns that correspond to the spacing between layers, the spacing between atoms across this direction. And we can measure then, again, the crystal structure and the crystal quality. So you can see these peaks here. This one corresponds to sapphire, which is the substrate that we grew on. And these ones here correspond to indium, or in this case, indium or indium nitride. And that's kind of the fun thing about science. Some people say that this paper, this peak in this pattern corresponds to indium, and some people said it corresponds to indium nitride. And who's right? It's a good question. Again, right here, special thanks to Dr. Diocampo. He was one of the professors at Georgia State who was not a physicist. He was in geosciences, and we needed access to this equipment, and he said we could borrow it. Or not borrow it, go and use it in his space. It was a little bit difficult to move. The last thing that I did at Georgia State was trying to understand the way that electrons moved around inside the material. This is basically a simple Hall setup, but we did it at a temperature of about 7 Kelvin, which sounds cold, but the lab down the hallway from us around the corner was working at like 5 millikelvin, or not, maybe not that cold. What was it? 50 millikelvin. They were working at 50 millikelvin. I was a little bit jealous, but I didn't get to play with those toys. So what I did with this instrument was that I would drive current across my sample. You can see here I have wires connected from here, and I'd connect wires to each corner of my sample. And then I could drive current across one and put a potential difference across the other and see how the current see how the electrons would move across the sample in a magnetic field as well. So that giant red thing back there was a big magnet set up to, I think, 1.5 Tesla. Not as high as you can go again, but it was fun to work with. One of the other things I did was atomic force microscopy. Now, Dr. Mattingly said I built an atomic force microscope. I always like to correct her. I didn't build it, I assembled it. They had all the pieces there, I just put them together. But it was still a very fun experience, and I did learn about a lot about atomic force microscopes at that point. And one of the things that you need to know about atomic force microscopes is that the tip that you're using matters. So an atomic force microscope, and forgive me, I should have had a slide in here, but I'm going to draw a picture. I didn't have a slide. I'm going to draw a picture. An atomic force microscope is basically like a record player. Now, records are old, but you guys might know the word vinyl. They basically work the same way a vinyl player works. They have a needle that drags along a surface, and if we have our surface down there, the needle will drag along, and then light will bounce off of it and measure what's going on. Now, when we're working with nice flat materials, like those last pictures I showed you with the pinholes and the spiraling around them, it works great. So you can see this top picture here. This is a picture of gallium nitride. It's wonderfully flat. There's a little line where the layer steps are going down. That's virtually perfect. that is ideal for what we want to do with these materials. When we're working with materials that are not ideal, like indium nitride, the shape of the material starts to mess with the way that the tip interacts with the surface. So if you're dealing with a tip that has a broad shape like this, and you can't get into the gaps between your materials like this, you can't see the material. You have to make sure that you have a tip that is sharp. And that way you can get in between each of these gaps. Now, that sounds simple, and it sounds like, yeah, of course you should know that. But when you're in the middle of research and you buy a $100 pack of tips and they're not working, you kind of forget some of the reasons. And you feel really stupid when you realize your tip wasn't shaped correctly. Lessons for the future. So what did we do? We used that special reactor to grow indium nitride above 650 degrees. You can see on the left there, our growth temperatures range from 700 degrees all the way up to 957 degrees Celsius. Now, the first question is, why wasn't this done before? And the answer is, it kind of was. The reason that it has been such a big problem is because every time they grow indium nitride, they always have hydrogen in the system, and hydrogen and indium nitride do not react well together. I don't know the exact reason behind that, but every study that comes out says if you have hydrogen, you get bad indium nitride. Back in, I want to say, the early 90s, they used a plasma source again to create indium nitride, and they documented that they could do it at 650 degrees, and then the project may have gotten abandoned or something, and pardon me, that was the last we ever heard of that result. So throughout my literature review, there was no information about indium nitride grown above 650 degrees that was successful. And that was very exciting because that means I got to publish a paper. And that paper became part of my dissertation. So when we grew these materials, you can see here, I got each of those characterization results for them. I got Raman results, and you can see on the left here, as I was talking about earlier, this here is the peak that's related to the crystal structure. And you can see as the temperature actually increases, I start to get some better crystal structure. This peak actually sharpens up. So you can see how it's nice and slow and broad over here. It gets a little bit sharper there, gets a bit sharper again. Here it's even sharper. And that looks great. The issue that we have, though, is that when we look at breaking this curve down into understanding what it is, we have to figure out what's going on. And we have two peaks that are actually related to the structure of this material. There is a broad peak. You can see this long, low, broad peak that is present in all of the samples. And in some of the samples, we start to see a second higher sharp peak. And that doesn't exactly bode well for my material, but it's not a killer strike yet. We took these results and we plotted them. So you can see here, it's a simple Raman again. On the left, we can say we plotted the E2 high, which is the broad peak. And you can see that broad peak actually kind of does, well, except for that one over there. It kind of does decrease and get a little bit lower, which means that my peak is getting sharper and there's less variance in the way that the structure is. I also took that sharp peak, and you can see that sharp peak is just so much sharper than that broad peak. Again, if I can get my laser to pop up, there it is. And it comes straight down, and you can see that just gets better every time the temperature goes up. And that's a great result, because that means that not only do I have indium growth above my decomposition temperature, but my indium nitride quality is getting better, or at least some of it might be getting better as I get higher temperatures. I took the AFM and I went to go look at the AFM, and I got this mess. This doesn't look good. You guys remember what I said I wanted my semiconductor to look like? Nice and flat, no pinholes, lots of steps. I don't see flat, I don't see pinholes, which is okay, I guess, but I don't see flat either, and I don't see those steps. We're producing what look to be indium nitride clusters or something on our surface. And we're sure it's indium nitride because we do have the Raman results that show this indium nitride peak on them. And we can see the results, 700 degrees, 800 degrees. They look pretty similar, right? We get up to 873 and we start to see these little speckles on top of it. So on the left-hand side, we're seeing about a 1 micron scan. On the right, we're seeing, left is 10 micron, right is 1 micron scan across. And you can see that more or less on the background, it looks the same. So on the right hand, I've just kind of taken a scan of the background. So I've looked in an area where there's not a lot of those speckles. And I get the same thing at 929. And when I look at 973, those big speckles are huge. And there's not really a way to get a good scan without some of that speckle on it. And I get, again, similar background, but now it's tainted by all these speckle things. And what we suspect is that those speckles, since they only appear in the 3 higher temperature samples, are related to this E2 high sharp. So we seem to be getting some material that is disordered, scattered across my surface, and we seem to be getting crystals that are growing on top of it. That's cool, but unfortunately, it's not what we were looking for. When we look at XRD, we see something similar. They all look very much the same. We get high peak, a sharp peak. We can model it with a little broad peak as well. Nothing interesting there. When we start to look at FTIR, again, you see we have the main peaks that are related to sapphire. So all the dashed lines are related to sapphire. And the features in between are related to indium nitride. And then we have these things over here. And according to literature, there's nothing in indium nitride at that energy level. So that's a problem that we need to understand. Moving on, we can model the thickness of these layers using the FTIR data, using the work done by a previous colleague of mine who graduated from Georgia State as well. And we can find that as the temperature increases, we actually are getting an increasing growth rate at a certain point, and then it kind of stabilizes or plateaus. We probably needed to get more data there to figure out what was actually happening at this point. But the fact that the growth rate increases as temperature increases is a very exciting result. That means that we are not just seeing some fluke of one experiment, but as the temperature increases, there is actually an increased growth rate of indium nitride. So there is some promise in this technique. And then what we went on to do was to measure resistivity. So I placed my sample in that reactor, in the chiller, and I connected up those 4 wires across the 4 corners again, and I measured the resistivity as a function of temperature. And this is where things started to go a little bit sideways. If I'm changing the temperature of my sample from 7 degrees to 300 Kelvin, I'm expecting to see a significant change in the resistivity of my material. Now, if you look at my graph on the left, I'm getting 8 times 10 to the minus 4 ohm centimeters, which is a reasonable result, but it doesn't really change. I'm expecting to see orders of magnitude change in that result. And we don't know why. I looked at the carrier concentration, and that is that energy levels. Remember how I can change move the electrons from the valence band to the conduction band? The carrier concentration says how many of those electrons are available to do that. And I look at the carrier concentration, and again, I'm expecting significant changes in the amount of carriers that are able to do that, but I'm getting very little change. I look at the mobility of these electrons, and the mobility is really, really low. I'm expecting values sitting above the hundreds, preferably. Predicted values are sitting at 20,000 for this material. So there is definitely a problem with my material. And I expected that. It's not flat, right? So what do I need to do? Well, one of the first things I did was I plotted the log of the resistivity as a function of temperature, or inverse temperature. And what this does is it lets me know when electrons become available to transition. So because they are locked in states, locked in energy states, as I increase the temperature, they can be, quote unquote, unlocked. They can start to move from a state where they're pretty much bound to their atom to a state where they start to be able to move a little bit easier. And I can find that value by following these 2 lines right here. And black on black was a bad choice. Don't do that. But by finding those 2 lines, it gives me gobbledygook. I'm getting energy or excitation energies of 10 to the minus 5 and 10 to the minus 6 eV, which means virtually nothing. If I blow on them, that's enough energy to move them around. And that wasn't helpful either. So what's going on? What is the technical definition of mobility? Mobility is how easy they move. It pretty much lies in the name. There is a lot of math that can be used to define that term. And if you're interested, I urge you to take solid state physics. You might be able to talk to Dr. Burdick, get him to discuss it a little bit in Phys for Sci, but I'm not sure if he wants to. So what I needed to do after finding these results, for these unexpected results, quite frankly, for the mobility, for the carrier concentration, is try to understand them. And one of the things that was interesting about these samples while I was working on them was that trying to do the AFM measurements of them did something interesting. You can see on the left here, we noticed that we were getting like a double image. And I am actually going to intentionally zoom right now. You can see over here, if you look at this picture, there's like an outline and then a second outline on each of these particles, each of those little clusters. And as time goes on, that outline, a double outline, changes until the image clears up. Now, what I've done with the sample was, let's see if I can get the zoom to go back in. There we go. What I'd done with the sample was that I'd actually grounded it. So we were not able to measure some of these samples at first because they just were not working, and we were getting this double imaging the whole time. We replaced 3 or 4 AFM tips because, well, you know, it could be the AFM tip, might not be sharp enough, might have broken it, who knows. And what we started to do was we looked at the phase of the AFM image. And what the phase does is it tells us how, quote unquote, sticky the sample is. And it turns out that the sample had 2 stickinesses. That's not a very technical term, I understand. But what happened was that the sample was interacting differently with the high parts of the tip was interacting differently with the high parts of the sample than with the low parts of the sample. And that actually changed as we grounded the sample, which means that that was an electrical effect. The tip was being polarized by the sample because the sample had stored up charge on it. And that's not supposed to be the case. These samples are not supposed to store charge on them. So this was very confusing, and this is where I am right now. I want to understand what was going on with this. We've observed that it can be grown at high temperatures, way above the decomposition temperature, at least what we thought was the decomposition temperature. The reason it can be done is because of the plasma. Every time that indium nitride was documented growing up in 650 degrees, it was always done in the presence of other things, like methyl groups, like hydrogen, like things like that. And what we did was we completely removed that from the equation. We changed it from working with nitrogen that needed to be changed to pre-changed nitrogen. We ionized the nitrogen before we even introduced it into the system, so it didn't need to have anything else done to it. And it made it significantly more reactive. The thing that I still want to do is move forward with trying to understand how the electrons behave on this material. That also means understanding this material a little bit better. That also means exploring what this material is capable of in its current state and trying to understand if we can get this material to a surface that is flat so that we can use it as a better semiconductor. So the scientific method, as I was talking to one of my friends this week, can sometimes be described as, oops, how did that happen? Wait, that was cool. Let's try it again. And that's where I'm at. We found something interesting that is unexpected, but we don't understand it. We can make it happen again, but we still don't know why. And that's where I want to figure that out. I'd like to thank some people that are not here. Dr. Nicholas Dietz was my advisor at Georgia State. And there's a black box around his name because he passed away while I was there. A message to my students and you guys who are not my students yet. But make sure teachers know you. Because the reason that I got to work with Dr. Dietz is because I was a student in his class, and I might have annoyed him, but he knew who I was. So when my previous advisor before him said, I don't want to work with you anymore, Dr. Dietz said, hey, I know that kid. I'd like to work with him. And when Dr. Dietz died, the same thing happened again. I was in Dr. Kozanov's class, and again, I might have annoyed him, but he got to know who I was, and he said, this research group who has this student in it needs someone to lead it, and I see something in these people, and I want to work with them. Dr. Giacampo was one of the professors at Georgia State who helped me with the X-ray machine. Dr. Lay was one of the professors who was new to Georgia State when I was there. He helped me with the Raman measurements. And then I would like to thank Mark and Zahir. They were my friends. They were people that I connected with. Zahir got a postdoc here in Chicago. He's working with a new growth method called, well, not new, but new to him, called, sorry, I'm blanking on the name. If you come and talk to me in my office, I'll be able to tell you. Daniel Seidlitz was a previous student, and Indika Kankamiga were also previous students of Dr. Dietz's as well. Carola Butler was the person who took the job that I used to have at Andrews, and she did it at Georgia State. So she was the lab coordinator. She would make sure all of the labs ran well and make sure all the equipment was in the right place at the right time. Something that I'd love to have here at Andrews, and I'm dreaming down the pipeline to do it, is a machine shop. People who can help you build the things that you need in the lab. And then there were the people that always helped with the computers, Justin and Jeremy. They were great guys. They always made sure your computers were running when you needed them. And then I'd also, of course, like to thank my wife and family. They've been with me for the last, however long the kids have been alive, and since I married your wife in 2007. It's been longer than 3 years. It is always great to have a partner that you can work with, and she has done that very well. As always, there's funding. I got a grant. Well, I didn't get a grant. My professors got grants from the DOE and from the NSF, and that was what allowed us to do this work. A lot of these things are very expensive. A single one of those machines cost over $1 million, those reactors. And I'm still trying to twist Dr. Mattingly's arm, although I haven't asked her for the money yet, to get some of the characterization machines for us here at Andrews. And that's me. Maybe a little bit fast, but we're good. Are there any questions? Feel free to type them in chat or to ask them out loud. You are on the speakers in the auditorium, so Dr. Summerscale, Dr. Burdick, and Dr. Kutzner can hear you, but it's fine.
Well, you were very